What is different from reinforcement learning to supervised learning? So in supervised learning, actually it's very similar to reinforcement learning. You can have picture as an input similar to the state observation, and you also have to predict the output. For example, here we want to predict where is a bicycle, car, traffic light, okay? And then you repeat the process of observing the data again and prediction again, okay? So the one of the most important thing that you have to know when you learn reinforcement learning course is that when should you use reinforcement learning and when should you use supervised learning. What is the difference between the two? So actually they are maybe more similar than you think. So the framework of supervised learning can explain here in the right picture. So in supervised learning, you get the training data as the input, okay? It's very similar to the state observation in reinforcement learning. And the model get the data, model try to predict the output, that is the labels. In reinforcement learning, you also have to predict the action, right? So it's very similar. And then the output here gonna compare to the labels in the training data, which is correct or error. And you're gonna learn from your correctness or your error, and you're gonna improve your model to be more intelligent based on your prediction and the true labels. In reinforcement learning, you also learn from the reward, right? So what is the difference? Here we show, two main difference between the two here. The difference is subtle. So in supervised learning, it also can be considered as playing a game in an environment, but it's a static environment. It means that the data is static, is fixed. It doesn't change upon your prediction. Whereas in the reinforcement learning, you action something, you change the environment, and you have different training data based on your action. For example, in Mario game, if you choose to move to the right, you're gonna get the screen gonna move forward, right? So the state of the game gonna move to the right. You get the new observation based on your action. But if you choose to move backward, if you choose to move back, you're gonna get the screen on the back. So the state of the game change differently based on your action. So in static environment, this is not true. The training data gonna be the same random data no matter what you predict. So yeah, so this environment in reinforcement learning, I call it explorable. Is that you can explore the environment according to your agent. The agent have to decide where to explore the environment, and the data is just different based on your action. And this is not true in the supervised learning. And also the feedback, actually the reward. The label in supervised learning can be thought of as a reward too, but it's useful all the time. You can use the reward, uh, actually the labels like a +1 if your prediction is correct, or -1 if your prediction is wrong. So you get the useful reward all the time, and you improve the model every time when you make a prediction. But in reinforcement learning, this is not true. You make the action, right? Mario move to the front or Mario move to the back, but you get most of the time zero reward. So it's called delay useful feedback. It means the useful feedback is got delay. You have to play for a while until your Mario die or win, that you get a very big reward. So the useful reward is delay. So these are like the two main difference between two frameworks. Okay, but you should use supervised learning first if it's possible. Okay, this is like a rule of thumb. As I mentioned, supervised learning model can learn with all the prediction, so it learns faster. Okay, so every time that you can frame your problem as supervised learning, you should use supervised learning first before trying reinforcement learning. Actually, for example, in Mario game, you can also frame your framework as supervised learning too, right? If you uh, as an expert playing the game and you capture all the screen, and then you know which state what should you do, right, based on the expert action, so you have the correct labels. For example, in the state of the game, when the monster come, you should jump. These are the correct labels that you can learn from the expert, and you can frame this Mario game as supervised learning too. Okay, so actually there are no like a clear boundary which problem is about reinforcement, which problem is about supervised learning. Many problem you can use both of them, but the main suggestion is that every time that you can frame your problem as supervised learning, I think you should use supervised learning first. Now let's look more closely about the two machine learning framework. Here, we take a look again at the supervised learning example, the object detection example. In this case, we have training data, which is a bunch of pictures, and we have learning goal. That is the label sets that we wanted to detect, right? So the bicycle, the car, person, and the traffic light, everything is known to the model. Model is trying to predict where is this object in the upcoming pictures. But in the training data, you also have to provide the correct labels. For example, the correct label of this car, bicycle, and every object that you are interested in is also, they are also in the training data. Okay, so in the supervised learning, you can also consider the static environment. That is the one that's gonna send the model the training data. Okay, very similar to reinforcement learning, but the process of sending the data is IID. It's come from identical and independent distributed. It means that the training data is randomly the same every time. It doesn't depend on the model action or the model prediction. So it's independent and identical. So the same every time and repetitive. Okay. This is not the case in reinforcement learning. So the training data, yeah, it looks like you have to provide a bunch of them before the training start. Okay, so the training set is fixed. You provide a lot of them, as much as you can, 10,000 or millions, better. Okay, more is better, and your prediction does not affect the environment. It means that your prediction doesn't affect the feeding of the training data. It's always IID, sampling the same time, the same thing every time. Okay, randomly sampling every time. And then, and then after get training data, the model gonna make a prediction of that training data, where and what object type in the picture, and then the environment gonna send the feedback, which are the labels to the model, and the model gonna learn immediately from that feedback. They are always useful. I mean, suppose the model predict that the car is here, but the car is not here, right? So the model gonna learn immediately from the correct labels. And if this car is not correctly predict, it's also learn immediately. Yeah, so it's update every time, every step. It's really fast learner in supervised learning setting. And just to make this diagram similar to reinforcement learning, we just group the two data together. The training data can be seen as sent together with the immediate feedback, with the labels. Okay, this is the label or the feedback from the previous prediction. That is, the model already predicts something to environment. The environment send the feedback, that is, you are correct or not, and also the new data, okay, together. And then the model learn from the feedback and make a prediction on the new data. This diagram actually is the same as this diagram. We just rearrange the sequence a little bit just to make it similar to reinforcement learning. Okay, and this is the reinforcement learning diagram. Okay, it's very similar to supervised learning. The environment now is not static anymore. But the same thing is that the environment gonna send you the data, the state observation. In the game, it actually also the screen, also the picture, similar to the supervised learning, the picture, and also the reward of the current state of the game. Okay, the reward of this current screen normally is 0. Okay, and then the agent have to learn from the state observation data and the reward, you see, and then make a prediction. So you see, it's very similar to supervised learning. The prediction, you see, it can be action, right? The next action, it can be move left, move right, jump left, jump right. It can be seen as classification too. So it's not so different from supervised learning. So what is the difference? Yeah, the first difference is that here the environment have to update based on the action, right? So you move forward, the environment have to update the state to the forward screen. But if you move to the right or to the back, the environment have to update, go to the backward screen. Okay, so the state observation in the next time step, it just depends on your action. This is the key. So that's why this is not IID anymore. So the data that you get depend on your action. This is different to supervised learning. And also immediate feedback, that is the reward, that is the result of your action, is a reward of the current state of the game. Usually it's nothing. For example, you move to the left, nothing happened, you get 0 reward. You move to the right, nothing happened again, you get 0 reward again. Until you die, until you play for a while, you die or you win, and then you get some reward, like a 10,000 for the win or minus 10,000 for die. But most of the time, you get no reward at all. Okay, so this no reward most of the time, also the key feature of reinforcement learning. So that is why this is different from supervised learning. You get mostly not so informative information, so it's difficult to learn. Okay, more difficult to learn compared to the supervised setting. Yeah, and in this reinforcement learning, the agent also have to choose action carefully, because the state of the game is depend on the agent action, right? So the agent had to choose to know more. Okay, sometimes it can win the game but not get that good score. Okay, it can keep optimizing known rewards, though it can keep playing the same thing and win the game. This is called exploitation. But it can also try something new, right? Make some random action sometime. Most of the time it's not good, but sometimes it can lead to the new discovery. Sometimes that new discovery lead to the winning with even more bigger reward. So this is called exploration. So all reinforcement learning algorithm have to choose this exploration and exploitation, balance between these two all the time. This is a key characteristic of the reinforcement learning, which is actually not the same in supervised learning. In this diagram, you can compare between the two frameworks side by side. On the top is the supervised learning. On the bottom is reinforcement learning. You can see that actually they are very similar. The different thing is that the one that I highlight. So the training data here is IID and repetitive. But the training data here is not IID. So the training data is themselves can be the same thing. The picture, the prediction can also be the same thing, like the class that you have to predict. So conceptually they are very similar, but the thing is that the data that you get from the reinforcement learning environment is not IID. It depends on your action, and also the feedback. It usually not so informative. Okay. And also another thing is that you see in supervised learning, we usually call our program as a model. So we make a model, we make a model to learn from environment and make the model smart. But reinforcement learning setting, we have to be careful not to call it a model, because there are two models here. The agent also a model. Environment is also a model. Yeah, because you can see that the environment have to process the action and update the new state and send the state to the agent. So this is also another model. And actually in the textbook, usually in reinforcement learning, when you see the word model, most of the time it is environment, it's not the agent. So in reinforcement learning, you have to be careful when you say model. Okay. And also, there are many times that you can combine reinforcement learning and supervised learning together. Yeah, it's like the sweet spot point that you can exploit the two advantages from the two frameworks. For example, the self-driving car problem. This is actually open problem. No one know how to solve self-driving car in real world at the moment. But if you think about it, it really look like reinforcement learning, because it can be thought of as a game. Okay, you make a driving game, you create a virtual world and make an agent to play this game. The state observation can be the camera, the front camera, the back camera, or the picture from the mirror, something like this. And then you can make the agent play game again and again. It can crash and die, and you repeat it again until it wins, arrive the destination, and make it smarter and smarter, play millions of times, something like this. But it's very slow in this reinforcement learning setting. In contrast, or in addition, if you use supervised learning methodology, instead of the raw picture to send to your agent, you can also add some information. For example, we just talk about the object detection, right? So you know the information from the object detection is very useful. So in each picture, instead of sending it in a raw form, you can also use the supervised learning first to detect, okay, in front of you, there is a car, there is a person, and the traffic light is red, so you have to be careful. Yeah, so now you know a lot of important information from supervised learning, and you can send this information to the reinforcement learning agent in addition to the raw pictures. So that is why in this problem, if you can combine, two machine learning frameworks together, maybe you get the best model. So in real world situation, it is depend on your imagination, which problem you want to use supervised learning, which problem you want to use reinforcement learning, or the two of them. It's just up to you. There is no right or no wrong answer.